Yes, I will talk about emerging hypernetworks in oscillator networks today, but I will try to really cover entire title of the conference. Yeah, so first let me start with this reconstructing network dynamics from data. Then we go through neuroscience and beyond. So why we really interested in reconstructing network dynamics, right? So we had actually a lot of talks about this, but what is the goal really? So what we want to do in general, so we would like to really predict future, right? So we would like to make some predictions and so on, then we can be ready for oncoming things, like predicting behavior is pretty important. And to do this, we need really a full functioning, so entire dynamical systems, equations and everything. But in many systems, we only have some data, and then they are coming from some points. Like we can probe data from this point, time, we can collect them and so on. And then to make prediction, there are some statistical techniques, of course, just learning this data and do some predictions, but which is not enough if there are some parameter changes and so on in the system. Like if there is any bifurcations and so on, it's very hard to predict with these statistical techniques. So which systems are like this? Of course, like neural networks, climate networks and so on. We can probe data, but we have no idea what is the structure, topology behind, interaction structure behind this system. So we would like to recover this. All right, so if we can recover this, then we have like G graph, we have F, isolated dynamics, we have H. This is basically how these nodes are talking to each other. Then after knowing everything, then we can do some bifurcation theory approaches and so on to track the critical transitions and so on. That's the goal. All right, so let's go to neuroscience a little bit. So brain is a structure, so consisting of many, composed of many clusters, and then each of these clusters are doing some jobs, some functionalities and so on. And there is another region which is called rich club, just connecting these places, these clusters, like sending messages and so on. And then in general, so like brain is working in this functionality, and then so to function, I mean, so this neurons in brain should get into some synchronization, also do some behaviors and so on. But if this rich club part is get into synchrony, there can be some pathological things. So what we want to do, we would like to abstract this brain into network structure, and then as you see, we do have these clusters around, and there is another red region, which is rich club, I say, so making this transfer, like knowledge transfer through these clusters. And if this part gets into synchronization, then we do not want to have this. So, all right, so how can we mimic really this? Then the idea is like putting some dynamics on these nodes, F, and then we couple them through a network, A, this is agency matrix, and then these nodes are talking to each other like with this H, and there is a coupling strand. We want to mimic neurons, then we have like a spiking dynamics, and then if the dynamics is spiking, if we are basically trying to create a setup for brain, then the coupling must be small, and in general this neuron dynamics is chaotic. Yeah, so it's all right. So under this setting, so if you simply collect data from every point and then apply some correlation techniques, then you get such a correlation matrix. Here are the node indexes, yeah, and then this is correlation between them. In general, you see no structure at all. Actually, this is a very well structured system. So it should be connected and so on. So there should be correlations, but due to small coupling, there is no correlation. Or maybe a little bit, but not showing any structural things in it. And then we tried this with different techniques as well, not only correlation, so like mutual information, some machine learning things and so on. So they are failing all. So they are not working. Then the question was, how can we tackle this problem? We do have some assumptions, and then these assumptions in general, again, coming from neuroscience. Like we know that, so we do have many poorly connected, almost independent nodes in our system. And then we do also know there are some hubs. Yeah? So this is the idea. And then very heuristically we can say, if these guys are poorly connected, they are really negligible, and then their coupling is really negligible, so we can ignore it. And then if these guys are basically having many connections to them, then there is a local mean field. Then we can say this guy has a mean field plus some fluctuations. Okay, so then the idea is this then. So if this is our equation, and then if we have like a little bit more assumptions, like if f is C expanding, so I said so we are going to use this spiking neurons, and they are not C2 expanding for sure, but like this is a like earlier work of than ours. And then if this H is small, and then if the network hubs are really well connected to the system, and then if there are many low degree nodes, then there is a theorem by Tiago, Sebastian, and Matteo. They are all here, 3 of them. And then you can write equation in this reducted mode. Yeah, so this is a reduction. And then what we have here new, we have this V, which is mean field. We have here a like noise part, which is basically finite size fluctuations. Okay, so what we have done then after this reduction, then so we can simply split our system into 2 parts, right? So this is deterministic part, and then this is basically noise. And then when we measure the correlation between these units, in general this deterministic part is chaotic, broadband, large amplitude. Because of that reason, statistical learning approaches all fails. Yeah, they fail, yeah. But what we can do, so I'm not going to go into details of this since today's main topic is not really this work, just the beginning of our research on network reconstruction. But if we can, if we use this reduction, and then if we know this network like scale-free network, like low degree nodes are abundant and the hubs are rare, then we can classify which node is low degree node, which node is hub. And if we know this, then we know, so what is F? We can learn what is V, then we can learn H, and we can learn more or less, so all these functions. The only thing left is network. If we know, so what is F and then what is H, then what we can do, we can simply filter out this part, and then we are only with noise. If we just basically remove this part from our data, then we have only noise. And then this noise really have the information, contains information, how these oscillators are talking to each other. And when you take the similarities, or like if you just infer who is really interacting with whom and so on from this noise, then you can get the network structure. Let me show this on an application, so which is a real world application. So like a data from 1993, cat brain, and then there are some like different functioning parts as I mentioned in the beginning, and then here this rich club parts, and they did this network abstraction from some measurements. Then this is the original network. Network has this somatomotor here, these green ones, auditory, visual, and frontal limbic, and these guys in the middle with this red circle around, they are rich club elements, nodes. So we put our neuron dynamics on this nodes, Rukov maps. Then afterwards we do simulations. Afterwards we forget about everything. Then we learn one by one what is F, isolated dynamics, what is H, coupling function. Then we remove this deterministic broadband part from the data. Then we have only noise for each node. And when we apply some correlation analysis afterwards, then we get an effective network. Then, so in the beginning, so I showed you, so if you simply check the correlation between nodes directly, then you get fully blue picture. But now we do have this structure, see. And if you threshold this, then you have a network here. And this network is not 100% the network, but super similar. So, and we do have some predictions there. For instance, as rich club is very important for us, we are looking for critical transitions to synchronization in rich club. Then we need to like also detect this rich club element nodes accurately. So our accuracy is not too bad. So we are only missing 2 nodes. I mean, so we do have extra 2 nodes. They're actually not in rich club, but we detect it like that. But this is not too bad to make predictions. I will show you now. But we had this alpha parameter, right? So coupling strength. So there we can really do this prediction. So this thing was also very important for us. So here on y-axis, we have prediction error. Prediction error is how much fail we do, I mean, so in this 2 things. Like, for instance, these guys should be pink, but we have green here, so which means this is a little bit prediction error and so on. And then for a coupling strength, various coupling strength numbers from 0.05 to 0.40, we can do this prediction quite nicely with like some prediction error, like 5 to 10 something. And then afterwards, we cannot do this prediction anymore. So only this part we can do. And then there is a reason for this. Right after this point, coupling, then system goes to synchronization, bifurcates to synchronization. Because of that reason, we cannot do it. Then, when system is functioning, yeah, so like as in desired function, then we can collect data. Like here is alpha, coupling strength. Here is synchronization, quality. If it's 1, fully synchronized. If it's 0, there is no synchronization at all. And then if we get data, when alpha is 0.3, then we have this kind of data. Then from here, we learn network dynamics. After learning network dynamics, so we make a prediction when the rich club will go to synchronization. We apply some bifurcation theory. Then we find this shaded area. Yeah? So this is our prediction. Then afterwards, we do this simulation for various alpha values, and we really see that the critical transition is exactly at this point. Yeah? So you see, I mean, the system gets into synchrony.
Can I just ask?
Yes, please.
Time series you use for the reconstruction, you simulate them based on the real network that you
Correct.
So
then afterwards we do reconstruction. After doing reconstruction, we predict when the system will go to synchronization. And then as we do have some predictions errors and so on, so we find like this region.
So you control alpha?
Yes. And this here dashed line is really the prediction from real system. So normally we know, I mean, so alpha C should be 0.42, and then we are finding like 0.42 plus minus some error, which is this dashed shaded area. Yeah.
Which alpha do you train the system?
Yeah, I mean, so we collect data from here when alpha is 0.3, then we reconstruct, we find this shaded area here, then afterwards we do further simulations, and then we see really our prediction works well. Yeah. And then this was the first, I guess, work at this for me. So first work for network reconstruction, and then we use this rule of oscillators in it, and then it worked quite well. And then we published this in 2020. Then after finishing this, then we started to think of some further projects. So about this, so what we can really do. So this, okay, rule of maps and so on, but if we can go like little bit more general cases or like different couplings and so on, so what kind of things we can observe. Then we again went back to the same position, like the beginning position of us. So again, we have network, we have the system, we do not know the interactions, but we would like to simulate this network and see if we can really do the job well. And when we did some simulations, of course, some ideological thoughts and so on, then we find a system. So in the beginning, although the system is pairwise interacting network, just a not normal network, when we get the data, when we reconstruct data, then instead of finding the exact network, we started to see some hypergraphs around. And then that was interesting, since like in these days, so probably you know, even this conference, I mean, so we saw many talks, everyone is interested in hypergraphs, which is sexy in these days, right? So then we wanted to understand, so why it's happening. And you see, so too many people are working, and then they say these hypergraphs are everywhere and so on. All right, very good. So hypergraphs is very good to model, but they can also just pop up from our classical networks. How it goes? Then we started to work on this, and this is our model again. This time we have differential equations instead of maps, and
Dennis, could you explain how the hypergraphs are popping up?
I will.
Your reconstruction.
I will.
Oh, it's a new reconstruction.
Exactly. So this is basically the observation what we have seen. Now I'm going to explain why it happens.
How you find the hypergraphs?
Yes.
How you observe them arising?
Yes.
Thank you.
Yeah. So that's this is just a brief, interesting observation for us. Then now I will show why they are popping up. Yeah. All right. So our model is this, and then here we have Z, which is state of the kth oscillator in complex numbers, and then this is F, which is isolated vector field, so from C to C, and then this is coupling strength, which is positive, and we have agency matrix A. If node I is connected to node J, then which is 1, other way around 0. So, and this is, as you see, pairwise, only 2 indices takes. And H is the coupling function. Again, pairwise coupling function. 2 oscillators connecting. All right, good. So this is the model. And then we choose our dynamics, isolated dynamics, close to a Hopf bifurcation, so which is given with this. This is the normal form for Hopf bifurcation. And we are basically using these parameters for our system. Like this proves work for gamma k equals lambda plus I omega k. And then here there should be some relationship between this lambda and alpha, since we want to have the system close to Hopf bifurcation, oscillate, and we do not want to break this oscillation. Because of that reason, alpha should be also selected carefully. And next assumption is this. So this omega case should satisfy some resonance conditions. I will explain now. All right, so this is not very important, and we have this beta k, and this beta k is same for everyone, and which is fixed to -1, but not very important. All right, so now let's play with an example, just a small simulation and so on. And we select here this pairwise coupling function in this form, which is a cubic polynomial interaction, right? And then this bar means it's complex conjugate. And then if we have this nonlinear interactions, we have further assumptions. This Jacobian should vanish at the origin. Like if everyone's 0, then this is 0. And we need to have satisfying resonance conditions, right? And then because of that reason, we choose our omegas like this. And then as you see, omega 2 is almost equal omega 1 plus omega 3, which is almost equal omega 4. This is the resonance conditions for us. And as I told you, so we need to choose this alpha and lambda also carefully. And then they are chosen in this way. Of course, so there is a room to change, and so somehow. But this is, for this example, so this alpha and lambda chosen as this. Then we go to simulation. Yeah, all the parameters are set, everything is good. So as I told you, so we are near Hopf bifurcation, systems oscillating nicely, and we have selected this lambda in this way. So the radius of this oscillation is about square root of lambda. Then alpha should be chosen accordingly. Then if I take this z, then afterwards write this unwrapped phases. There is a linear increase first. Right? So if I just basically go to polar coordinates, then I can go for phases, and then phases are like this, unwrapped ones, they're increasing. What I want to do, I want to play with the interactions, so I'm not really interested how they really grow fast. Because of that reason, first I find this linear increase, not increase, so linear increasing rates, then I remove them, they are omega k's, from my data, and then I get these phases. Yeah, they are more stationary, they are not increasing. Then what I want to do, I would like to reconstruct this new case. Then what I have, basically I have the system. And then I'm trying to reconstruct back the system from this data. How I solve this problem? So then this is my derivative of my data, and then here is like a matrix, so containing a lot of functions and so on. Then there's a basis basically, and then from this basis I want to find some coefficients. If I find these coefficients in a good way, then this should give me back to the equation, my original equation. How I do this? So using this compressed sensing idea, so we put all these 4 oscillators we had, like 4 oscillators data are here, and then we create this library, like many functions, trigonometrical functions and so on, in a row, and we put our data into this function, we create our basis. After creating this basis, then we want to regress, we want to learn the coefficients. And we apply this compressed sensing, which means sparse regression idea. Yeah? So Tiago mentioned this problem quite in detail. Basically, we do some L1 norm regularization. Yeah?
What sign of two variables mean here?
These are?
Yes.
Yeah, so this sign of two variables means like linear combination of them. You can, like, there are many like options of these things. Like sine nu1 minus nu2, sine nu1 plus nu2, and so on. So many combinations, yeah? And then this is very long matrix. So you have, I mean, so very large library. And then you do same thing for this triplets and so on. So basically, you try to create super large bases. And your model can contain these ones. And you want to reconstruct your model in a sparse way. So you want to basically get your model as sparse as possible. Yeah?
Can I ask also, where did you stop? Triplets? Because you have 4 systems?
I mean, you can go further as much as you wish. So here is like triplets in my presentation, and then if you go here, like you can go to 10th order, I don't know. So.
Okay, but you stop at triplets for this case, right?
For this case, we stopped at the quadruplets because we have 4 oscillators.
Most part.
Yeah.
So it's not clear.
So the complexity is in terms of the number of nodes, like in theory.
Yeah. All right. So, and then if you do this reconstruction, then you find like just few numbers for your constants. Yeah? Then, which means if you basically put them now at this point, then you reconstruct your system. But in the beginning, I mean, so we know we started with these constants are very small because we simply removed the linear trend, right, from the equation. These are very small now. And we reconstructed our system with these triplets. And then that was very interesting for us because these really slow oscillations coming from the system. And in the beginning, originally, so they were all pairwise interacting nodes. But right now, we do have only triplets. We have any pairwise interactions in our network anymore. Which means we started from here and then we ended up here. So, and the question was this exactly. So why these hyperlinks are appearing in the reconstruction? Yeah. Now I'm going to Gary's question. So this is again, I mean, so the simulation, so what we have seen and so on. Now, how it happens. As I mentioned, so this is a sparse reconstruction, which means we are trying to find like a simple definition of this formula. Yeah? Simplest description of this dynamical system. If it is the case, then first thing to do, of course, check the normal form, right? In general, normal form gives you the simplified form of your system. Then what you do, of course, you apply a coordinate transformation of the form wk equals zk minus alpha p kz And then here pkz is basically some form of some polynomials like this here. This is nice, since from reconstruction we know, so there shouldn't be any pairwise interactions. Applying this then solves the problem for this part, for the coupling part. You do this coordinate transformation, then afterwards you get your new monomials. And then from these monomials you check, so which one are in resonant, which one are not resonant. And then you then remove all these non-resonant terms and so on. Then you get with you stay with only resonant ones, and then they are triplets and very good. But you need to apply this transformation to isolated dynamics as well. Whenever you apply this to isolated one, then system is, so the reconstruction gets very crazy, right? So from here, then now you start getting some pairwise interactions. You also need to remove these pairwise interactions. Then what you need to do, then you need to apply, so then this transformation generates additional undesired terms that you do not want to see in your normal form. Then what you need to do, you need to apply a second coordinate transformation, the same form. This is very tricky. So this is really a combinatorial problem. And then to tackle this problem, we introduced a special bracket form. And then in this bracket form, so we could really track, so who should be there, who shouldn't be there, and so on. So this allowed us to solve this problem. And then that was Eddie's idea. So Eddie is also here. And I will not go into details of this thing, but I will invite you to Eddie's poster, so which is just there. And if you want to talk to Eddie, so how he really tackled this problem and so on. So he might maybe help you better than me, and maybe I do not need to spend too much time about this. And but using this idea really helped us. So how to find, so non-resonant terms and resonant ones. And using this then gave us a very nice formula, very nice, like a set of rules, what kind of connections or what kind of motifs are resonant, what kind of motifs are non-resonant, graphs, subgraphs are non-resonant. So we, just to show this, so I'm just giving you examples from node 1. And then according to this rules that we found, if you have like this guy with the, I guess this is negative frequency, then if you go this one and then afterwards the other one, like which means the similar ones are not directly connected, but if any other one like in between, the opposite sign one in between, then this is a resonant term. So another example of resonant, which is actually similar, same thing. So again, first one is connected to fourth and then this connected to third one. So this is also very nice. This is a resonant as well. And if you have something like this guy is connected to two others and then they are in like opposite signs, then this is non-resonant. This is very algorithmic and very nice. So we could really like write all the possibilities and so on. And then another thing that you need to check that might be resonant, like this starting from this guy going to blue, opposite sign, and then afterwards 4. But if the network is not connected in the original, this is also forbidden. So although this is resonant, but it's not appearing, then you need to drop this too. And then using all these algorithms, then you can really write this equation, normal form, which is exactly in the form that we found from sparse regression. Exactly same. So which means we have this algorithm here, coming from these brackets and so on, very complicated things. And then when you have this network, when you have these frequencies are written and so on, you have this rules, list of rules, then just basically asking your system which ones are resonant, which ones not resonant, then afterwards you can write down the equation, which is also provided in online, so with the publication, so I will show you now. And what you need to do basically, you just need to write what kind of agency matrix you have, and then what are the frequencies of these guys, and then if they are really satisfying the conditions, then our algorithm give you back to this normal form, which is fitting very well with the data reconstruction. Very good. Let's see so how it works. So this is data. we simply simulate our original system. We get the data. After getting this data, we know this parameter, right? So we can simply linearly combine this phases, and then we get this. So since they were appearing in our normal form, and then they were appearing in our like reconstruction, and this is data. And then if we simply go and then take the initial condition from here, put into our normal form description, then if we simulate exactly the same data, then they are really fitting perfectly. And if you zoom in, you see, so the data is really fluctuating, and the normal form is just basically fitting it. But this is very expected, right? So this, in machine learning, many people are talking about this overfittings and so on. To avoid this overfitting, what they do, so applying some L1 norm and so on. Then if you do this, instead of learning all the switching points and so on, or jumping points, or all the fluctuations, you only learn the envelope of the data dynamics. And this is well enough. I mean, so this is what we are really looking for. Why this is really coming from this sparse regression, compressed sensing. All right, nice. So now we covered network reconstruction and we discussed neuroscience. Now time to go to beyond, right? So we are covering all the entire title of the conference. All right, so what is beyond? So I mentioned, so I explained this problem in one SIAM meeting, like I guess 2021, right? Last year. And then afterwards, so Istvan Kiz was there. He is very nice, neat chemist working in dynamical systems. And then he said, look, so this is very good results. And then we can maybe design an experiment to simply get a similar data set. Then we can, basically he challenged us. So I can give you data, can you reconstruct this as you have done in your numerics? Then he prepared such an experimental setup. I am totally not experimentalist, so I do not understand too much this. When I saw this, so I couldn't say too many, I couldn't make any comments. Then afterwards, he provided me something like this. Oh, now this is way more clear for me. Yeah? So like there is a network, and then these guys are interacting in like, as we had, like in our example, right? So it's a ring again. And for coupling, we had some complex conjugates. And then to make these complex conjugates, as far as I understand, so they need to add some delays in experimental setups. They were always all new to me. This is fine. And then I'm only interested in this part, as I told you. Now we did this experiment. And then after doing the experiment, then we get the data from these points. Yeah? So from each guys. And then this is color coded, but I'm not sure if you can really see the colors. All right. So frequencies are also, so as we used, so everything is same. Whatever we did in our numerical test, so he simply used exactly the same numbers. If he couldn't use same numbers, then he gave us new numbers, and so we can something like this. So, but everything is same. So in numerics, we are using whatever we're using. So Istvan is using in his experimental setup in a way. Then you can measure these potentials from this. Then there is a way to compute the frequencies. Yeah, and then after doing some like standardization, so filtering and so on. Again, so experimental people know more these things. Then I got these red lines. And then afterwards, we applied our technique. It, boom, came exactly the same networks that we found. Yeah, so it was totally fitting with our theoretical things, simulations, and then also experimentally. All right, so we were very happy. Then we keep digging in, yeah? So what kind of interesting things we can find in this? So, like Sandro did, so very end of the talk, so you are trying to connect this to synchronization, yeah? So actually everyone did, right? So more or less, so talking about some theory, and then at the end you come to synchronization. So a new example, we change our coupling function. So now coupling function is quadratic instead of, yeah, so this time just quadratic one. Then these are the parameters. Again, I mean, so resonance conditions are satisfied and Jacobian vanishes at the origin and so on. So which is pairwise coupling function again. So like this classic network, just network ring topology. And as you see, I would like point this again. This coupling is not diffusive. Yeah? So basically, if one oscillator running away, other one is not following it. At least intuitively, it's not like that, so for sure. Or it's not trying to catch up, yeah? So oscillators are not trying to catch up each other. So with this coupling scheme. Then we do our magic again, so we use these rules. And then after doing that, apply normal form and reconstruction, both same now, since we are sure, I mean, so reconstruction and normal form give same results. And this is the reconstructed hypernetwork. But interestingly, for this kind of coupling, now we have triplets, like this yellow one. We have this, this is yellow one and this is green one, right? And then, which is basically two hyperlinks. And between 1 and 2, there is another resonant term, which is pairwise. So this kind of network basically we found at the end.
So these ones are directed, right?
I mean, like, yeah, so.
I mean, is it just visually or are they?
I guess just visually. So I guess this one positive, this one negative. Yeah. If I'm not wrong. So, but yeah, or other, vice versa. Yeah.
Is it kind of master-slave here? Like 3 and 4, they do not force 1 and 2?
3 and 4 are not forcing.
I think that's what happened.
Yeah.
3 and 4 were enslaved by,
Yeah, this kind of hyperinteraction. Basically, these two of these guys driving this, which means like you do have these 4 differential equations, and then the fourth one, you see there is a effect of 1 and 2, but if you go to first oscillator's differential equation, there is no effect of 4. So this kind of interaction. But basically the link on oscillator 4, node 4, is hyperlink. And then if you go to first oscillator, then the coupling is basically between 1 and 2. Yeah, clear, I guess. Then when you basically do the simulations for different delta and alpha parameters, coupling strength, here's the delta. The delta was, so this guy here, so mismatch parameter in these frequencies. Then you get a synchronization tongue. So, and then this region is synchronized. And then these white ones are not synchronized. So with respect to my synchronization error here. And theoretically, you can find this synchronization is depending on like alpha proportional to square root of delta. And this also perfectly loops. In the beginning, so it was really not intuitive for me at least. So to see such a synchronization phenomena in this system with this type of coupling. But at the end of the day, so we have this hypernetwork construction. And from there, we can theoretically, can really predict where the system will bifurcate synchronization. All right, so far so good. So this was another interesting application to me. Then the next one was this. So, okay, everything is fine. This is showing really interesting results, but we do have some limitations. We do always use nonlinear coupling, right? So in general, I mean, so we do also have linear coupling also. So, and we did try our technique like on this KURAMOTO models. It's a modular network, yeah? So this here, I mean, so these guys are all connected in this red region, and then here, all these yellows are all connected, and then they are coupling constant between them, mu, and then they are really KURAMOTO oscillators. and so on. And then like interclusters, we have alpha coupling strength. And then in this case, if we apply some mean field, so like Otantenson reduction, then we have like this 4 guys are connected to each other, right? So at the end, we can write the system as it is, as this way, I mean, so from mean fields. And then when you do the reconstruction from these mean fields, again, so you find such networks, which means, although there is some limitation to be in this nonlinear one, but whenever you check for this mean field and so on, then this brings you some nonlinearity. This nonlinearity is enough to reconstruct this emergent hypernetworks from this system. And then this is basically exactly the same thing. So really frequencies from this real system, and then the reconstructed hypergraph is matching perfectly. Of course, there are a lot of like fluctuations in this underneath oscillators, like fast oscillations, but we can detect the slow oscillations very accurately. All right, so, and then this is also appeared like just a few days back with Eddie, Tiago, and then I'm here, so Istvan, and then Jorge, they are in San Luis University, US. All right, good. So what is take-home message? So we managed to uncover this mechanism to describe this emergent higher-order interactions in oscillator networks using normal form theory. And when we apply this normal form theory, then the pairwise interactions can be eliminated under some resonance conditions after some coordinate transformations. And they are rising really triplet interactions, at least if we have these nonlinear interactions in the original network. And this higher order interactions is actually, interactions are really natural, typical, right? So from this, this is really clear from these normal forms. And then if your couplings are nonlinear, and if you apply some sparsity to reconstruct the systems, you only find the envelope of this oscillations, slow oscillations, then these hypernetworks can be really found. Yeah, this is very natural. All right, so that's it. Hopefully I'm in time. Thank you very much.